Hi all, I am Shweta Lokhande, a researcher working on the planning of sewerage infrastructure in cities.
Hi everyone, myself Parmeshwari Tirodkar, a curious student and responsible citizen.
In this video, you will learn about various configurations of wastewater conveyance which are vital for sewerage infrastructure planning. Welcome to our city. As you are all aware, cities typically consist of various types of areas and building typologies, such as residential buildings, where people reside, and depending on their standard of living and types of houses, residential areas are classified as high income, middle income, and low income housing. Then there are commercial buildings, from where businesses operate, and these include offices, shopping centers, and restaurants. There are also institutional buildings such as hospitals, schools, and transportation hubs. Also, cities have public spaces or recreation places such as public parks, gardens, and common waterfronts. Depending on the city, some industries or factories may also be present where goods are produced or stored. At times, agricultural areas may be present near the city's fringes. There are several water bodies near or amidst the city.
Hey, but why are the water bodies so polluted these days?
Unfortunately, this is true. Water is a lifeline we often overlook. The urban water systems are the unsung heroes that keep our cities hydrated and thriving. And how it is managed can greatly impact our daily lives. The water and wastewater utilities have a key role to play in urban water management. As for all citizens, it is important to understand how water interacts with different parts of the city.
Water interacts with city? What do you mean by that?
Well, let us understand the present approach of water provisioning in cities and its environmental implications. Cities have residential areas with household consumption, commercial and institutional demands, agricultural landscapes or recreation spaces, industries, and various natural water bodies. We have an electricity grid to provide energy. Every city has a mix of all these elements having various water demands. Typically, fresh water is transported from long distances to meet the domestic, agricultural, and industrial needs for the development of cities, which involves huge transportation costs and consumes energy. Conventionally, agriculture involves indiscriminately using artificial nitrogen fertilizers, and the fertilizer production is highly energy intensive. Additionally, urban citizens are increasingly consuming synthetic detergents containing phosphorus. Furthermore, apart from domestic sewage, the modern lifestyle of urban citizens has introduced emerging contaminants through pesticides, insecticides, cosmetics, toxic wastes from industries, etc. All of this consumed water finds its way to the centralized sewage treatment plants.
Hang on. Did you say centralized sewage treatment plants? What are those?
Yes, you heard it right. Let me explain to you the various modes of conveying domestic wastewater, that is, sewage. Practically, every region has a variety of settings such as rural, peri-urban, and urban. Even in an urban city, there may be pockets of informal settlements or a diverse housing typology. Some cities might have adjoining agricultural or industrial areas. The sanitation service provisioning varies in different areas according to the sanitation infrastructure, that is, the type of toilets and whether the different wastewater streams are separated or combined. Accordingly, the wastewater characteristics vary in different regions. Some areas might have on-site sanitation facilities with either land-based treatment or household in-situ treatment. Some areas may have on-site storage, transport, and treatment of wastewater. Usually, in cities, sewage is transported through sewer networks and collected in sewage treatment plants. The portfolio approach emphasizes that a mix of the above-mentioned sanitation options could be relevant for a city or a region, and selection indicators beyond economics should be used to choose the appropriate sanitation option as per the ground situation and decision-making context. whether rural, peri-urban and urban or even dense urban, to achieve various outcomes such as the Sustainability Development Goals. The portfolio approach provides an opportunity to achieve universal improved sanitation sustainably. Usually, in cities, sewage is transported through sewer networks and collected in sewage treatment plants, which should be the aspiration for all the cities. But how to do it sustainably is a big challenge. Sewer networks can be adopted in a centralized or decentralized manner. Let us understand the difference between these configurations. Typically, designers use the centralized sewer network as the primary approach. Centralized sewerage infrastructure implies that the domestic wastewater or sewage is collected from the entire city or region under consideration. There are house connections, laterals, main sewers, and trunk sewers that finally carry the wastewater from far off distances to a single point of treatment. This results in a single large capacity of treatment plants, and since it is difficult to find a large piece of land within the city, sewage is often transported away from the city to the outskirts for treatment and subsequent disposal. The key advantage with centralized approach is that the scale of economy is reached for large-sized wastewater treatment plants, making wastewater treatment cost-effective. Biological treatment systems also function well at a large scale. It allows for streamlined operations, implementation of advanced mechanized technologies, and sophisticated treatment processes, thus ensuring high water quality and consistency.
Given the advantages of centralized infrastructure, why is most sewerage infrastructure failing? And why are centralized treatment systems being criticized?
There are several complexities, and every coin has two sides, right? So, if you holistically look at the region, we are unnecessarily transporting freshwater and wastewater to long distances in the process of centralization. Firstly, we spend tremendous energy to fix nitrogen for artificial fertilizer production. Next, the nutrients nitrogen and phosphorus enter the cities through food cycle and other products we use in our day-to-day lives, which find their way in the wastewater. If the sewage treatment plants fail to function or do not perform up to the standards, untreated or partially treated wastewater enters the water bodies and causes eutrophication. Also, it is difficult to achieve water circularity in centralized systems as long redistribution networks might be needed to be constructed. Hence, only a small fraction of treated wastewater can be recycled or reclaimed conveniently and cheaply. Thus, for cities aiming to integrate circular economy practices, centralized systems are not favored. Although centralized infrastructure is commonly adopted due to the scale of economies achieved in sewage treatment, it attains a diseconomy of scale in sewage conveyance.
Diseconomy of scale in sewage conveyance? What do you mean by that?
To understand that, you need to think from a systems perspective. The sewerage infrastructure comprises of sewer networks that collect wastewater and sewage treatment plants. The overall life cycle costs of sewerage infrastructure thus comprise of capital and operation and maintenance costs of the sewer network as well as the sewage treatment plants. The network cost constitutes a major share of the total cost, but the centralized STPs are driven considering scale of economy and treatment, which constitutes 20 to 30% of the project cost. Although in some cases, the costs of centralized and decentralized configurations are comparable, decentralized treatment systems provide several intangible benefits that are not currently captured in the assessment framework. This economy of scale in sewage conveyance means that as the sewage system expands or serves a larger area, although the treatment cost per unit of sewage treated reduces, the cost per unit of sewage conveyed increases due to factors like longer pipes, higher maintenance, and more complex infrastructure. Although centralized treatment is cost effective, it leads to massive investments in laying the sewer network. The sewers are laid at a slope for using the gravity. Hence, long sewer lengths lead to deeper sewers. Especially the trunk sewers are laid at large depths below the ground. The construction of these trunk sewers involves massive excavation, and such mega projects often result in huge delays. Additionally, these sewers are difficult and costly to maintain in the long run. Complex equipment and machinery are needed for cleaning the choked sewer lines. Sometimes, even machines fail to remove the blockages, and sanitation workers are forced to enter the manholes to clean the sewers. Despite the legal ban on manual scavenging, it is still practiced in cities, as evident from such news articles. Thus, the deep sewers in highly centralized systems pose safety issues to workers responsible for cleaning the sewers. Moreover, extreme centralization comes with significant risks, as they are highly vulnerable. A single large-sized STP serves as a single point of failure in case of equipment malfunction, a natural disaster, or an act of vandalism. And this can disrupt the wastewater treatment services for the entire city. Just imagine, how detrimental would this failure prove to the nearby water bodies where untreated wastewater is being disposed? They would be prone to reduced levels of dissolved oxygen, affecting the marine ecology, and also prone to eutrophication.
Oh, I understand now. As per my knowledge, decentralized infrastructure is the alternative for centralized systems, right? But what do you exactly mean by decentralization?
Okay, now let us explore the decentralized network configuration. In this scenario, there are several STPs for the city or region under consideration. The STPs are located very close to the point of generation of wastewater. This eliminates the long sewer networks and facilitates simultaneous implementation of multiple STPs. This reduces the overall time of implementing the project. Moreover, each of the served areas may have different water demands and hence different wastewater characteristics. For example, wastewater generated from the residential, commercial, and industrial land uses may differ slightly. Decentralized treatment facilities can uniquely be designed as per the wastewater characteristics of the region.
Oh, I see. Is that the reason why decentralized infrastructure is being propagated by researchers nowadays?
Yes, there are several advantages of decentralized systems. Especially if the cities are to adopt a circular approach for water management, decentralized systems are highly suitable. They serve as alternate sources of water, which can be used for secondary purposes such as toilet flushing or landscaping. Also, if one STP fails or encounters an issue, it impacts only a small area, not the entire city, as the sewage treatment service is disconnected among all STPs. The different STPs can adopt location-specific sewage treatment technologies.
Okay, so as I understand, decentralized configurations are pretty resilient. They should definitely be the way ahead for infrastructure planning, right?
You are partly correct. However, decentralized treatment systems also have certain limitations. Managing and maintaining numerous independent systems can be costly and cumbersome for wastewater utilities. If two small-sized sewage treatment plants are planned using biological treatment, the STP tends to fail or incurs substantial costs, as the scale of economy is not attained in small-sized plants. In case of lack of ownership by the households or residential dwellers in operation and maintenance of STPs, governing a large number of STPs might become a huge challenge for the wastewater utilities. Thus, coordinating the effective maintenance and ensuring compliance with regulations can be burdensome for the regulatory authorities.
Now it is becoming very confusing. You mean to say both centralized and decentralized infrastructure have limitations? Then what should be the approach for planning sewerage infrastructure?
I understand your confusion. In this regard, we at Srishti Lab in IIT Bombay have developed the concept of appropriately scaled decentralization. I assume that by now you are at least able to appreciate the complexities of planning sewerage infrastructure. You see, when we talk about decentralized systems, it can mean several alternatives. So, deciding the scale of implementing decentralized infrastructure is very crucial. As we discussed, extreme decentralization also has its own challenges. Let me explain graphically. In this figure, the x-axis represents the scale or extent of decentralization, On one side, there are highly centralized systems, say at city scale. On the other hand, there are extreme decentralized systems, say at building scale. In this figure, the notional trends of each driver are represented, which are normalized on a scale of, say, 0 to 1. The life cycle cost is highest for centralized systems due to large infrastructure scale and intense energy usage. It reduces as we move towards decentralization, but again increases due to increased number of sewage treatment plants. Social benefits in terms of local employment opportunities and community participation are higher in decentralized systems. The potential for recycled water is higher in decentralized systems where water is treated at the source and can be used at lower redistribution costs. Efficient resource recovery depends on source separation, which is better achieved in a decentralized system. But for resource recovery to be economically viable, some scale is needed, which is sought somewhere in the middle. The environmental impacts are higher in centralized systems due to intensive use of energy. It reduces and again increases towards decentralization due to higher resource consumption in decentralized STPs. Ease of governance is also considered to be maximum at the center, as the complexity of outsourcing and commissioning the projects increases for larger centralized systems. Also, operation and maintenance cost can become cumbersome for too many systems and is hence better achieved at community scale than household level. If all these trends are superimposed, the sustainability drivers can somewhat be represented like this.
Oh, sustainability is such a complex phenomenon. Understanding it itself is so difficult. I'm sure quantifying it must be immensely challenging.
True that. Not just sustainability, there's more to it. You must have heard of climate change, right? Climate change is a global challenge. Sustainability is associated with optimal usage of resources with least impacts on the environment, while resilience is associated with the response of urban water systems to extreme conditions, disasters, or events of failure. Further, with respect to resilience, robustness denotes the ability of treatment systems to withstand disturbance without compromising service. Large-scale systems are more vulnerable to service disruption amidst failures. Adaptive capacity refers to the ability to recover from stress and restore service, and smaller systems are easier to install and operate within a short time. Further, flexibility involves ability of the infrastructure to respond to changed objective, for example, new norms for water quality or mandatory recycling. Phasing of infrastructure plays a key role in this regard, and decentralized systems can facilitate a flexible design. Overall, resilience can be better achieved in smaller systems, wherein damages are restricted to the local level and can be almost constant till a scale is reached beyond which it reduces. Considering the sustainability and resilience aspects, it is observed that the ideal zone for achieving both is somewhere in the middle, and this is regarded as appropriately scaled decentralization.
Now I understand the significance of appropriate scale. But how to decide the optimal scale of implementation?
Interesting question. In literature, different scales of decentralization are mentioned. So, by optimal scale of decentralization, we refer to the scale of clusters that can be made to achieve maximum benefits. We propose this scale of decentralization to be proportionate to the size of the city in terms of sewage generation in the area. For example, if a city has a total sewage generation around 500 million liters per day, that is 5 million population equivalents, then constructing sewage treatment plants having a capacity ranging from 20 to 30 MLD, that is around 300,000 population equivalents, can achieve a reasonable scale of decentralization. Presently, these numbers are based on limited research and data, but it's the approach that we are putting forth, the approach of moving towards the optimal zone, and it needs further research to establish these numbers. Moreover, it's not that there exists one correct number for an optimal scale of systems. The idea is to avoid too small and too big scale systems by adopting scaled decentralization. Planning an appropriate scale for implementing sewerage infrastructure is the most crucial aspect of decision making, which needs to be understood by planners, consultants, and decision makers. The scale of STPs will further impact the choices of treatment technologies at a particular location. These decisions have implications in the long run and affect the infrastructure sustenance and finances significantly. By implementing scaled decentralization, we can strategically eliminate the trunk sewers that comprise a giant share of network costs. The approach of appropriately scaled decentralization can enhance resilience through decentralized water management and also gain the necessary scale of economy. Such an approach can ensure adequate and optimal usage of resources spent on infrastructure creation.
I see. So, scale decentralization is also context specific. But what about treatment technologies?
Oh, now that's another box altogether. It's a long discussion. But to answer your question briefly, there are several types of treatment technologies which broadly can be categorized as mechanized treatment systems and natural treatment systems. On one hand, we have mechanized treatment technologies requiring less land, but those are energy intensive as they require oxygen for bacterial degradation. The continuous aeration requirements result in heavy operation and maintenance cost for operating the wastewater treatment plant. In addition to elevated costs, the high energy consumption results in greenhouse gas emissions. In this manner, in the process of addressing water pollution, we end up causing air pollution. Another concern regarding centralized STPs is that highly skilled labor is required for operation, which might not be available everywhere. However, mechanized treatment systems are preferred in regions having adequate funds, skilled labor, and land constraints. On the contrary, there are natural treatment systems that mimic the processes taking place in nature and hardly require energy. These technologies can employ low-skilled labor, can be managed by local communities, and are aesthetically pleasing. Natural treatment systems have relatively higher land requirements, but could be planned strategically in the given settings. Additionally, considering the trade-offs between the two treatment approaches, mechanized and natural, these could be combined strategically to gain the advantages of both approaches, and this concept is called hybrid treatment systems. The scale of implementing sewerage infrastructure surely influences the choice of wastewater treatment technologies. Interestingly, scaled decentralization could be achieved by both mechanized and natural treatment systems, and the decision needs to be taken on a case-to-case basis. Not every technology is appropriate for every city or context. In this regard, using multi-criteria decision-making techniques based on a comprehensive assessment using a wide number of indicators is needed, and decision support tools such as Jal Vishwa could be used for determining the appropriate configuration and treatment technology depending on the local context. By adopting scaled decentralization and appropriate wastewater treatment technologies, we can create sewerage infrastructure that is both resilient and sustainable. The various elements of city, such as land use and building typologies, can be used to plan the sewerage zones and facilitate urban water management in an integrated manner. Scaled decentralization approach can also be used for retrofitting the existing sewerage infrastructure in cities.
Yes, planning sewerage infrastructure certainly needs a bird's eye view due to its complexities. Thanks a lot for such an elaborate explanation regarding this crucial topic.
Thank you for joining us on this journey of understanding the complexities of sewerage infrastructure. As a responsible citizen, it is crucial for us to understand where does our sewage flow, what does it take for the wastewater utilities to maintain the networked infrastructure. Sewerage infrastructure is often invisible, but it is highly complex and demanding in terms of skill, knowledge, finances, and resources. We should be aware that it comes at a huge cost, and as a responsible citizen, we should be willing to pay for sewage treatment. the choices and decisions we make today will contribute to a better and more water secure future. Thank you.